Hello, I've decided to do the notes for 4.2 by just looking at the completed notes. Partly because, well, mostly because the main reason is the graphing limitations. I can't graph in real time and record it on this device. So I'm just going to talk through these notes. You can fill them out as if you want, or you could just use these as reference moving forward. Obviously, I'll also have the posted completed notes as part of the assignment. So first off, 4.2, this is essentially an extension on quadratic functions or quadratic equations. So first off, what we're looking at in this section is graphing quadratic functions. We want to be able to find the vertex, the axis of symmetry for quadratic functions, find the min and max values and intercepts of a quadratic function, and then determine inputs that yield the maximum or minimum value. So why did I circle values here? Inputs are inputs x that yield, meaning that give us a max or min. And if it's a quadratic, if we see right here, quadratic, let's say an upside down facing parabola, the input x1, and this is just like terminology to make sure we understand what it means, the input 1 yields a max of 10, where 10 is the max. So the output is the max and the input yields it, or it may say produce, or where the max occurs. So what we'll see different within this section is these three type models right here, where we have for the first one here, it's a quadratic with a square root. If we look at this, it's a quadratic cube rooted. And then lastly over here, we have a quartic, a fourth power, where it's a fourth power term, a squared term, and a 1. And what we're going to do is look at what do these graphs look like relative to the original quadratic, x squared minus x, so plus 1, and how we can still find the minimum are what inputs yield the minimum or maximum value. So if you look here in the directions, it says find the input that yield the minimum value or values, and then compute the minimum. So this is saying find the x value of the input or of the vertex, and then compute the minimum would be what is the output of that. So if we had just x squared minus x plus 1 without the root, that would be a quadratic. It'll look something like this, and you could check it on your graph. Now, if we plug in a square root of this, we end up getting a graph that looks like this, right? Because if, let's say we have like an input of 5 here. If you square root, or an input of 5 gives us some output, which would be up here. And if we square rooted that would make it a smaller value. So instead of our output being up here, our output would be right here. So this is our x squared minus x plus 1, and then this is our root x squared minus x plus 1, where we actually find that these values near in the middle section here will actually be larger. But what we do find, if I graph this accurately, and you could check it on like Desmos, if you type in Desmos calculator, or simply your calculator TI-84, you'll find that the vertex, the input, will be the same for at a half, and again, this graph isn't graphed 100% accurately, but if we did negative b over 2a for this, which gives us the x value of the vertex, we would get 1/2, and that is the same x value that will give us the vertex, quote-unquote vertex, for this new function. So essentially, the long story short is, for all three of these functions, you still are going to do x equals negative b over 2a to find the value that yields your minimum or maximum value. And then instead of plugging it just into the quadratic, you're plugging it into the actual function, which will give us a different value. So the question may be, why is this root function higher here than it is down here in terms of the output? Well, let's go ahead and look. First off, if I take b, which is negative 1, and a, which is 1, and plug it in, we'll end up getting a half. If you plug a half in, that would give you 1/4 minus a half plus 1, which ends up being 3/4. Now, 3/4 is 0.75. If I square root 3/4, I end up getting root 3 over 2, and root 3 over 2 is about 0.866. So when we square root a fraction that's less than 1, that's between 0 and 1, it makes it bigger, and that's why the output is bigger. But in any case, the input that yields the minimum for this one is 1/2, and the output is root 3 over 2. So essentially, you're doing the exact same thing as you would do for a quadratic in terms of finding the negative b over 2a to get the input, and then to get the output, you just plug it into the function with the root. Same over here, we'll have the same type situation happening. Again, if I do x squared minus x plus 1, I do negative b over 2a, we'll get 1/2. And then if we cube root 3/4, that will give us a little larger value, and we could just write it like that, or if it says an approximate form, you just plug it in the calculator. Now, if we look at this last one, if you think of x to the 4th as x squared squared, and x squared as x squared to the 1st, this is actually a quadratic. You can think of this as a, or some other variable other than x, so I have a here, and you think of this as a, and if you look, this is a quadratic. And it works to get us the a value of 1/2 if we think of x squared as 1/2. But then our variable, remember, is x to the 4th, or if we, like I said, we substitute a in for here, a equals 1/2. Well, then we have to set x squared equal to 1/2, because if a is equal to x squared and a equals 1/2, then x squared equals 1/2. Another way you could look at it is if I have my normal quadratic of x squared quadratic resolves to, so let's say, for instance, if I have x squared plus dot dot dot, to find your vertex, you do negative b over 2a. If you look, the relationship of the power of the function versus the power of x here, it is the square root of that. So same with x to the 4th. If this was x to the 4th quadratic like we have up here, note it won't work for all quadratics. It only works when you have this pattern here of x to the 4th, x squared, and then a constant, because then you can think of it like this. So then we just simply have x squared equal to negative b over 2a instead of x equals negative b over 2a. So all that being said, if you square root 1/2, you'll get plus or minus 1 over root 2 or root 2 over 2. And that explains our graph here, where for the original quadratic, we would have 1/2 is the value that yields your minimum. But for this quadratic, which I graphed, and you can check, it gives us W-type figure, we have 2 different inputs that yield a minimum. But it was still the same process to get the x value that yielded it, except it was x squared equals 1/2 versus x equals 1/2. So then once we have plus or minus root 2 over 2, that's the x values that yield your minimum, you go ahead and plug that in to your function. And when we do that, if you look, root 2 over 2, whether it's plus or minus to the 4th, would just turn positive. Same here, plus or minus squared would also turn positive. And this right here, this would be the 4 in the index of 2 would go to 2 squared, so that'd be 4 in the numerator, divided by 16. And then here, this would be 2 over 4. And then if you simplify that, 1/4 minus 2/4 plus 4/4 gives us 3/4. So that means both of the inputs of plus or minus root 2 over 2 gives us 3/4.